I think you'd say, both in terms of historically the length of work units that we do, the fact that we distribute multiple different applications. At one point, I think we hit a high point of 13 different applications that we're actually all distributing out to our volunteers. And of course, that we're very linked to the science that we're doing. So we will have high points on different applications being run at different times. So from the point of view, though, of performance, so as part of the project, we did a little test. So we submitted 500 member ensemble looking at a particular weather event, UK Storm Desmond, which was quite destructive in the UK. And this is the graph that we're now able to produce looking at our batch. So median runtime, 5.5 hours. Queue time, well, the high point, bear in mind, this is on our development site, not on our main production site with a limited number of machines. We queued for about 21.5 hours. But, we're starting to think about, starting to present to people, how quickly 50% returned, how quickly 80% returned, so we can start giving people an understanding of how our batches are starting to behave. But these are producing hundreds of megabytes of output every 5.5 hours. So this is one of those questions that it comes to, of how we exactly make sure that we manage what goes into a particular work unit in terms of diagnostics. So this involves working very closely with the scientific team, because in theory, you could generate gigabytes of data per time step. That's obviously something that we don't want to happen from our volunteer point of view. That's the fastest way to guarantee you have no volunteers. If you overload what they're expecting, both in download to their machines, because obviously this also talks about the ancillaries, but or configuration files, but also what they're then expected to upload. So just quickly, from a science point of view, this was one of the results that we actually showed in the launch of the service for that Storm Desmond, to the extent then that in the workshop where we launched this, we then did another study as well, looking at a different extreme weather event, and there just over 3 hours. So one of the things here, this model as a whole runs incredibly fast. From our point of view, this is something, we've had something similar in the past, our HAD AM3, our global weather at home, where we've managed to flood the network somewhat with tens of thousands of work units by accident. It's one of those low points when you're explaining on the moderator email list of, we apologize that we managed to completely flood everyone's machine. A bit embarrassing. But the important point is, these are hours in terms of runs, and this is something that we're going to have to get used to in making sure we understand how we configure these work units so that they're able to be utilized, so that our volunteers don't get flooded with data. So again, here's some science. So this just shows actually, so 50 members is the standard ensemble size that the ECMWF use in terms of their production. And you can see the improvements. This was looking at mean sea level pressure, and we can see the shape. You can understand much better the shape of that pressure dip for that tropical cyclone as it moved from the Gulf area, and it ended up actually over in Norway in the end. So one of the other things we've done for this, because we're working with a new community. So the aim with this new project is not to work with the same bunch that for ages with a new model, but to actually bring a new set of scientists on board as well. And there, one of the things that we've done is actually created a dashboard to allow them to interact much more easily with the project, because up until now, it's been much more a case of more personal interactions, particularly with Sarah, who's the coordinator for CPDN for the whole of the project now. So we've started to look at, okay, how can we actually more better integrate the scientists in their processes with our processes? Because one of the interesting challenges that we have is, I showed the figure earlier with the connection with all of our sites, all of our partners around the world. Now, if something goes wrong with one of those sites, which is where we're distributing data for the most part, volunteers see that as a failure. they won't be able to upload their resulting work units or the like. The challenge from our point of view, though, is they don't see it as a failure. I'm going to pick on Oregon here because I can. They don't see it as a failure of Oregon. They see it as a failure of Oxford and CPDN. So we have to understand how we work with our remote partner sites to actually ensure that where we have those relationships, where we have those issues, we're able to solve problems quickly. But yeah, so this is how we present now, and everything that the scientific team need to do can actually be accessed through this dashboard. So moving on, so core services. So from the server point of view, we did migrate we've gone to version 1.0.3 of the server. This is a staged upgrade and worked very well, so we would thank the server team for that, because overall, it's in the past upgrades, we've delayed upgrades in the past because of the concern about interruptions to service. We've got still some updating to do, particularly around website code. Data volumes are still the significant challenge, and in a moment I'll show you that they've become more of a challenge because we're about to do another migration. But one of our big problems is we calculate our volunteers' credit afresh every single time that we recalculate credit, any credit at all, from work unit 1. It's a painful experience to the extent now that we only recalculate credit on a much less frequent basis than we've done. And it's one of Andy's and my big challenges going forward for the next few months, is changing the credit calculation and probably moving away. One of the reasons for the recalculation is around recent average credit. That's one of the reasons why the calculation was so complex, and we're going to move away from that. So last year, this was the infrastructure that I put up, displaying how the vast majority of our services were all run within a VMware cloud operated by our own department. We then had a set of upload services that were located around the world. We were using some physical machines. We had within our university center a set of systems that were hosted there as well. We've had some changes since then. So you'll notice it's a lot simpler. We have cut away a lot of our machines that were unnecessary. The other thing, and I'll talk more about this red cross in a moment, because is that we've moved away from our data coming back to Oxford. So what we've done, and the thing down the bottom is very important for those at the back. I apologize, it's so low. Ah, yes, the screen's all around. So things inside the red square are our core services. So our scheduler, our download, our database, all of that, which was running within the OERC cloud. We are going to be migrating this to something called the Jasmine Cloud, which is owned and operated by the Natural Environment Research Council, by STFC, by Rutherford Appleton Laboratory, for the environmental sciences community. So we're migrating away from our physical infrastructure, from our cloud-based physical infrastructure in Oxford, into the cloud within Jasmine. The reasons behind that I've put on the slide. The infrastructure in Oxford became end of life a long time ago, and in a bit of a, I could speak marginally, in a bit of a break with the agreement that we sort of had with our department, where we bought service from them. They didn't then really actually upgrade the equipment and be a service provider. So from our point of view, we were just running on older and older kit. The unfortunate thing is that's made our service pretty unreliable. We've had a non-trivial amount of downtime, and as a consequence of that, we have had some very unhappy volunteers. And I'm sure Richard was here; he could tell you about some of our unhappy volunteers in greater detail. The aim is to migrate to someone who is operating a service, who will provide some things for free, but depending on who the funder of the projects are. but also has a realistic pricing structure for actually paying for some of the services that they provide. So, data management. So I'm going to walk through, so a small change, sort of change of gear here really, talking about, making project more visible to the volunteer and scientists. So what do we actually do in terms of how scientists interact? What's the workflow they go through? But then at the end, what does the volunteer do? What does the volunteer see? So when we start off, so, what's the workflow, for the scientist? Well, the very first thing they give us is a very complex XML file, and I'm going to scare you with some XML now, which details the experiment. It is in a standardized format. So there's, and most of the scientific team that we've been working with for the medium to long term know everything about this. So they can edit these, they pass them back to Sarah and the application submission team, so that, so from that point of view, it's well understood. And it tells you everything about all of the experiment that's actually going to be run, all of the work units that are going to be distributed. And it's long, and it has every single one of the work units are basically described on an individual basis. So as you can imagine, when we launch multi-thousand member ensembles, these things are very, very big. So one of the things we've done, and I linked through from that dashboard from the OpenIFS project, was actually create a form for people to actually fill in for the OpenIFS project. Because as I said, OpenIFS was intended to not only give us new capability, to bring new scientists on board. So what we wanted to do is give them the option immediately of an easier to use mechanism. That includes, actually how they understand what configuration files their work units might need. And if they need to upload new work units, when we have, for the whole of the project, we have a mechanism for people to upload into our repository, the configuration. So we, of course, then distribute our work units via BOINC. Everything's downloaded in the standard manner. And we then present our batches. So our work goes out in batches, and we've organized the set of web pages where we can track, monitor, and understand all of the different experiments that we're actually running at any time. Is the 50 most open recent batches. You can see here actually that Meredith's been very busy. If you look, they're all Meredith's batches. Meredith owns them all. But, and you can also see that this was quite some time ago. We were on batch 806. I think we're on about 850 some now. So, from our point of view, this is an awful lot of work going through at any one time. And we need to understand, the level of success and the level of failure of our individual work units as they're going through. But of course, this is what the volunteer sees of work units. They see the BOINC client. Unfortunately, this was mine, and as I run a Mac, I couldn't actually click on the tasks because at the time we weren't running any Mac-based work units. But when I look back in history, all tasks for David Wallam, then I see my task has a ridiculous number. And so from that point of view, the visibility for the research for the volunteer is really not great. It was also, there was a bit of an issue for a while as well. So, but of course, once the volunteers finish computing their workloads, they send the result to a predefined upload server, which can be located anywhere in the world. We never expect 100% of our work units because we work with very large batches and understand that, from that point of view, some of our the machines won't be returning, but we look for a largish return. We do regenerate failed work units. And then once we've got what we think is a satisfactory number for a particular experiment, we close a batch, and then all the rest of the work units are out there are set to not wanted. But what happens next? What happens when we've got all this data? And I'm going to talk you through one particular project, one particular experiment. So the winter storms in the UK in 2013 were particularly destructive. We had lots of areas flooded. We had, the wettest month on record. We had some of our railway washed away. Down in Dawlish, it's very pretty. It runs right along the coast, an area where they get Atlantic storms. Right along the coast, it falls apart. Not great. From the Environment Agency, they talk about, millions of pounds worth of damage, thousands of people displaced, things like that. Sites, 7,000 hectares of sites of special scientific interest affected, 5,000 people affected by flooding, and, historic. It was a very significant issue. Our Prime Minister at the time, he stood up and said, the floods are affecting large parts of the country are probably connected to climate change. So one of the questions that immediately came around was, well, can we prove it? Or could we prove it? Now, one of the things our project does where we talk about attribution, so extreme event attribution, is we talk about this in two ways. We never say a particular event was caused by climate change, because you can't do that, because that's a really bad question, and normally there's such variability that's not going to work. But what we do is we effectively talk about things here. Did human-induced climate change modify the probability of this event occurring, i.e. the change, can we attribute a change in risk, or did human-induced climate change contribute to the severity of the event? Attribution of magnitude. And to do this, we, of course, launched a fair number of work units looking at a particular weather at home. And if you look on here, you can see down at the bottom, this batch has 174,397 work units that were successful. And this is the details for batch 52, the batch that we used. And our analysis was very successful. We got a Nature climate change paper out of it. So, the lead author and the person that did a lot of the work on it were very happy. Our newspapers picked up on it because we actually did this project live. So we were linked. So every day, Sarah basically did a load of analysis and then sent the plots to The Guardian, who then put them on The Guardian website. And so from that point of view, the impact of this study was huge, because not only were we answering a question that our Prime Minister had asked, which is always something nice to be able to do, but we were doing it in real time, and we weren't presenting the results at the time in an esoteric manner. We're actually putting it straight through the newspaper. But then once the study has ended, the paper's been published, then one of the parts, of course, is what do you do with the data? So one of the things for the batch information, which has a lot of CPDN for specific information in it, but it actually has something here, archive status published. So that tells us, right, okay, so from that point of view, this batch has been used in a publication, and we need to archive this. So the first thing we did, we of course used our friends in the Centre for Environmental Data Analysis at Rutherford Appleton Laboratory, who were really happy to receive our 52 terabytes of data. So from that point of view, so we uploaded the data to them. And then the next thing that we did, because we believe in open data and the idea of fair data, is we also did a Nature Scientific Data publication to describe where this data could be got, what the processing had been done to this data, and everything else. So in the end, we had two high-impact Nature publications. And we've started recording and presenting all of the publications that have come out of CPDN. We present them on the website, and the things that we've also been doing alongside just a list of publications, because every project should be doing this, we've also been linking through to the batch of data that's actually been used within that publication. And here are those two publications. We've got Human Influence on Climate Change in 2014, Southern England, and the Ensemble of European Regional Climate Simulations. But what we've done is we've gone a little step further than that. What we've also done is we've created a page where our volunteers can actually go and look, and it's volunteer specific, can go and look and see which batches they've actually contributed work units to. And hence, and this is Jim, one of our moderators here, who's been awfully active. So he can see that successful batch contributions, data that he's generated has actually contributed to all of these publications. So we're now saying not only are you contributing to CPDN in an abstract manner, you're actually generating, this is your contribution to these scientific outputs. And here they are in Jim's, here is both the Schaller-led publications. And from our point of view, this is an incredibly important thing. The thing with BOINC when compared to other citizen science type things is we're not asking people to use their brain power to classify pictures. In some ways, we're saying, well, you just connect your computer and then you sort of leave it, and that's sort of it, and you contribute to science. And it's still can be a fairly abstract concept for people. And I think in some ways, this is one of the reasons why we might be seeing a drop-off in volunteers with some of our projects as well, because we're not making that last step connection. And that's one of the things that we're really aiming to do here. So
they have established a system of badges where I can see on my own account page live list of publications and in fact my proportional contribution within the ensemble of the project. And also every time I post on a website a brief panel of my badge achievement is there for all to see, which enables everybody all in the project to see in advance what everyone else is doing, assess the person that helping got message or otherwise that contribution. And having live there in the account
So one of the things we did think about when we were doing this was initially, Sarah and I had a little discussion about saying, well, actually, whether you put on here how much somebody's contributed to one of these papers. Jim might have contributed, and this is just for argument's sake, 5% of the work units. And actually, the problem with doing that in some ways actually is that no one volunteer is actually going to be contributing anything more than sort of a very, very small amount of a percentage point, because we still have a fair number of volunteers. So from that point of view, we thought, well, in some ways and Sarah said to me, well, what are you going to do? Tell people how little they've contributed, because that's what it'll look like. And yeah, we could rank them in how many papers. From our point of view, what we wanted to do was give people encouragement by saying, look, this is how much you're contributing. If we started ranking people, or it just sort of, it felt for the amount of extra effort it was going to take us to introduce that system, and maybe from the point of view of the contributions on the forums, this might be something to do rather than the actual number crunching. It just felt, we wanted to celebrate everyone's contributions, even if some user went to this page and had one paper here, they should still feel exceedingly good about the fact they've actually contributed, to academic output and to furthering the knowledge of mankind from that point of view. So just to finish off, we are still the world's largest climate facility by some way, and actually we're increasing through new models. We are aiming to build with that new model, broadening the scientific user community, broadening the number of, broadening the number of funded activities that we do as well, because actually getting funding for computing people, because all of our core team is not core funded by our university, it's actually funded off the projects that we get. So we have to be very successful in getting and participating in funded projects. We're going to be migrating the core service to something, to a community cloud, aiming to improve reliability. Data is still our biggest problem. We've got 249 terabytes of data at Rutherford Lab. We've got about 200 terabytes of data on spinning disks still on our cloud within Oxford. We've got about 150 terabytes of data on tape. And that's just the 2 data centers that we directly control. The other 10, we have not an unknown amount of data, but probably a comparable amount of data at least 2 or 3 of those. Particularly actually our Australian data centre, located the Australian National Data Service. Linking volunteers to scientific output, what we're aiming to do here is use this as a way of boosting volunteer retention. From our point of view, we're very happy with the number of volunteers we have, because our queue of work units that are waiting to go out in general is never that large. We want it to see that there is some queue, because as soon as you have no new work available, then volunteers start going, oh, well, I might go and find a more active project. So we want a small queue, but not no queue. So from our point of view, but we don't want people to go. Keeping people on board, and in some ways, really pulling on the fact they're contributing to, what is man's greatest scientific challenge at the moment. That's a key thing for us. We're generating science on a regular basis, creating societal impact. And I put this in as a link. I'm going to see if this works now. Yeah. So on the BBC World Service, Science in Action. Oh, that's not come up on that. Sorry. Let's come over here. Our most recent analysis was looking. There's been an enormous heat wave in France over the last 2 weeks or so. And so we contributed through the World Weather Attribution Project to the analysis of this heat wave. And if you listen to that program, there's a discussion with contributions from CPDN scientists, and and there is a link down to our climateprediction.net project at the bottom. So from our point of view, we are, this is, heavily relevant scientific analysis that we're doing in real time. So just to finish off now, let's go back to this. I have to thank an enormous number of people. I can get this out of the way. Our colleagues in the Environmental Change Institute, my other colleagues in the Volunteer Computing Group, Atmospheric Physics, the Met Office, the European Centre for Medium Range Weather Forecasting. Very importantly, our moderators, who are hugely important. And I think an interesting point is our volunteers are those that run a lot of our models. Our moderators, not only are they running some of the models, particularly on the development site project, where we're able to test our work units before they run out, and of course the rest of our public. And these are some of the organisations that we collaborate with on a regular basis. Thank you very much, everyone. Question at the back.
With the 2 last examples you showed with the snowstorm and heat wave, those are no data sets in response to something, right?
Yes, so the World Weather Attribution Project actually does these analyses, these attribution analyses in real time. It was originally funded by an organisation called Climate Central, who wanted to put a climate piece on every US weather network report around any particular extreme event that was happening and have an analysis. So we completed the analysis of the European heat wave before the heat wave had actually probably finished. So the aim with these is what we term as rapid attribution. Yes, so we have, so there's 2 things. We have something called climateprediction.teach, which is a link off of CPDN, which is around, links into certainly the UK's syllabus around climate. And from the point of view of can anyone submit a project, or can anyone submit a request for analysis, the data that we generate is open. So from the point of view of can someone use the data that we generate? Absolutely. Can somebody request, as it stands at the moment, anyone submit work units? No. The reason for that in some ways comes back to this point that the core team, the infrastructure, is unfortunately all on soft money. So from our point of view, we have to prioritize and do prioritize the running of projects that we're actually funding, Andy, Sarah, and the bit of Meredith that's within the OERC. And so, the flip side of that is the data is open. So from our point of view, people can request the data set. One of the parts also, the analysis code, there's a set of analysis code actually that Sarah wrote and is available in GitHub. And so from that point of view, so the other part of this is, of course, climate change is an incredibly politicized topic, maybe more where we're the country in which we're standing at the moment than others at the moment. But, from our point of view, it's not we don't want to control the message, but what we do want to make sure is that there is some understanding around, what we're trying to show. So it comes back to that thing, the ill-formed question about a particular extreme event is always the one of climate change caused this event. And it's like, well, actually, no. There's a whole host of reasons why this particular event, but as we say, it may have made it bigger, it may have made it more likely. And that's the sort of things that we're really able to show at a modelling stage at the moment. From a more interesting point with the OpenIFS, the weather forecasting and application is particularly that. Actually, it's around, we are aiming to do weather forecasting, and that is something where, we are looking to see, how that data set might be more used as well. Yep. Oh yes, sorry. Yep. So yes. Okay. Yep.
So regarding the data concerns on the military side, is your concern of just slowing down their internet access at the point, or are you concerned about the total data transfer?
Total data transfer, because so we've sort of imposed over the lifetime of CPDN. Oh, so is there what's the concern with the question is what's the concern with regard to data volumes from the point of view of volunteers? And it's really a case that CPDN has over our lifetime imposed a sort of a self-imposed thing that we don't want our volunteers to be having to download for any one work unit more than about 100 megabytes. We don't really want to upload more than about 100 megabytes per work unit. That's fine when your work units last a fairly large amount of time in the day, from the point of view of days. If you stick with those same restrictions, but in work units that last, single digit number of hours, all of a sudden your total data transfer can step up enormously. So what we've got to work out is how we still are able to do the relevant science that we need to do, but that we can actually maintain somewhere in the region of something sensible in terms of data downloads and data uploads. One of the points of this might be, for example, there's the targeted hosts capability, and to say, well, okay, you do run multiple work units that are longitudinally split, but you all send them to the same host, for example, or that you temporarily split, but you then make sure that the next stage goes to the same host that ran the first stage, so that you don't upload restart files and things like that are pretty large. So we've been trying to work out a number of different strategies for very fast work units, because we never designed CPDN for work units that last, that are so quick. If that was because everything ran for days and weeks. Our weather at home runs it takes about a week, maybe a bit longer than a week, to run one of our weather at home 1 year work units, and they use about the same volume of data to download for configuration and return about the same amount of data that one of our OpenIFS work unit does in 3 hours. Matthew.
I was curious, you mentioned a lot of your discussion was about the volume of data at the end of this various places where it's archived. I wonder how much that data is used and what you envision people doing with it, if they aren't, in addition to what they're already doing.
So the questions around what we envisaged maybe that people are going to be doing with data that we generate above and beyond the studies that they're actually meant for. The biggest problem actually is that from a funder point of view, we are constrained. So there is a requirement that all data generated by a UK UKRI funded project must be kept for 10 years from last use. So there's a straight funder requirement that we must keep our data. We've been a bit inventive in the past about what we actually mean by that, from the point of view of, well, do we keep the raw data or do we keep subsets? And we've kept subsets in some cases and we've kept raw data in others. From the point of view of what we envisage people will do with this data, so the data's stored in a self-describing NetCDF format. So we, from the point of view of accessibility, interoperability and reuse, the data is arranged in the perfect manner. If you're another scientist that's looking, say, for example, at the winter 2013-14 storm, there is a data set there ready and waiting with, over 192,000, I think, was in the end that we produced ensemble members. So the data is in a community, well-funded, well-supported community repository. So what we'd hope is that people are searching for that, and that's one of the reasons why we put the Nature Scientific Data publication in. One of the problems around data reuse very often is accessibility. People don't know these data sets are there, so they just go and try and regenerate it. We've already had, we have a project that's funded at the moment by the National Trust to look at climate change impacts. So National Trust, it's like an organisation that looks after historic buildings and things in the UK. It's not quite a government organisation. It's a sort of quasi-governmenty sort of thing, which I know sounds a bit odd. But they're very interested, obviously, in how climate change is going to affect them long term, both from the point of view of impact on buildings, impact on some of the natural lands that have been bequeathed to them, and whether or not their visitor numbers are going to change and things like that. If you go and search on the National Trust website, interestingly, they have a whole page looking at the 2013-14 floods, of how much impact was actually to their infrastructure, to things that are in their charge. So we've been talking to them and long term about saying, well, okay, let's use the data set that we have to analyze and look at what was the impact for your infrastructure. From our point of view, we make data sets available for people to then use, and it might be, as per the question earlier, actually giving it to schools. So I'm going to give a talk at a grammar school next week about climate change and impacts on infrastructure, and we'll be taking a little bit of data and some of our analysis code to show how we analyze data and how we create some of these results to 17 and 18-year-olds. Never done it before. It'll be really good. So, yes. Yep. Not so. Not particularly. One of the things we've actually been looking at, and I've had last academic year, I had a 4th year undergraduate project looking. So the question was around whether or not we've identified commercial or industrial activity of relevance to the climate change impacts that we've seen. So we've had a 4th year undergraduate project looking at impact on the UK rail system, the UK energy system, transmission energy system, of future climate scenarios. So if we do keep to Paris goals of 1.5 or don't and go to 2 degrees, what's the impact on the energy system going to be from the point of view of heat waves and wind? And, so those sort of studies, we've got another 2 people coming in to do further projects looking at rail infrastructure and road infrastructure. And there is there is a whole set of activities, some government supported, some not, looking at future climate scenarios and utilizing some of the data that we've generated. So there's a very big project called HAPPY, Half a Degree of Anthropogenic Warming Prognosis, Products and Impacts, which actually fed into the IPCC special report on 1.5 degrees, and particularly as a data set that's now being used by a very large number of people to look at some of these things around impacts, both from a sort of a natural environment point of view, an infrastructure point of view, and more generally.
Have you also worked with some companies, like the insurance company, right, who actually take the climate or weather change as the key parameters for their pricing strategy or business model to kind of integrate some of your research findings?
So historically, the question was, have we worked particularly with insurance companies, because insurance companies often use climate as one of the key things around risk. Yes, so we do this in two ways. The first one is generate a data set of realistic extreme events. So we quite literally run a very large ensemble. We then subset it to just give them a data set containing realistic extreme events. And that's, that might be any extreme event type. And we did that working with Zurich Insurance, and we gave them a pretty large ensemble in the end. And that was funded by them and is used in their pricing strategies around risk. We've also had discussion around whether or not we can put some of the other points around changes in magnitude and changes in frequency into pricing models, but that hasn't really got any further. Sarah can. Oh, to get the value. Yes. Okay.
All right, I'm going to say that more questions for CPN. We continue at lunch. We have one more presentation. John, about how long is this? All right, so I'll work it over. So we will encourage this conversation to continue over lunch, but we're going to let Sean present on ISO.
No. Right.
I'll just say that, generally speaking, when I'm at conferences and workshops, I always wind up hating the person that saves me in my lunch. So I'm Sean, and I'm going to be standing between you and your lunch. So, thank you.
That's the live stream.
All right.
All right. So we're going to go from the most important scientific challenge facing mankind to Einstein at home, or finding spinning things in space.
Gravitational waves around the BBC page. So it's the climate stuff here. The gravitational waves down lower.
I did not notice that.
Yeah,
Okay.
I'd like to do segues. Yeah. Well, we just got a good PR. I'm not sure what's like that. We lose all. They don't know. I think Bruce is.
Does it have to be like dragged to another screen sometimes?
Are you clicking?
Yeah, I am. There it goes. I just took a little bit more up. I don't know why. This is a really old machine, so David, if you wanted to test a slow machine against current working, this is a good thing.
All right.
Hopefully that works.
Thank you, Keith. All right. So I'm Sean, and then I am affiliated with the University of Wisconsin-Milwaukee, and I'll be talking about Einstein at home.
So Einstein at Home, of course, is a BOINC volunteer computing project. It searches for astrophysical signals from space. Specifically, we're talking about spinning neutron stars, or pulsars. It uses the data from the LIGO experiment. It also uses data from the Arecibo radio telescope, as well as the Parkes telescope, and finally the Fermi Gamma Ray telescope, which is a satellite. So to this end, we distribute a few different applications to our volunteers. Basically, there's a gravitational wave search, which is based on the LIGO data, and then a number of pulsar searches, which is based, right now it's mostly based on Fermi and the Arecibo data set. The Parkes data set has already been crunched, if you will, but will talk about it in brief. Just at a glance, these are sort of statistics that I pulled from our server status page, right? So total number of users, I mean, we've been around since about 2004, Vern? Yeah, so, right, thank you. 2005, so, in that time we've had, nearly 500,000 users, 1.7 million hosts. Pretty much every single country is represented, a tremendous number of work units and a tremendous number of teraflops. In the past 2 weeks, about 30,000 hosts, about 239,000 CPU cores. This GPU number, the GPU core number, about 18,500, is from the last 7 days. So this talk is basically, I'm just going to talk briefly about the science, and basically we're going to talk about pulsars and what they are, because I'm just going to make the assumption that none of you have degrees in astronomy, so I don't know. Good assumption? Okay, good. Then we'll also briefly talk about LIGO and the gravitational wave searches. Then onto the technology, which is about the BOINC side of things. Why volunteer computing? What lessons we've learned? And what do we do to keep our volunteers engaged? All right. So in brief, pulsars are highly magnetized neutron stars. Other stellar objects can also be pulsars, but for the purposes of this talk, they're basically neutron stars. They rotate, and their radiation can be observed from Earth. The analogy that we always use is that there are lighthouses in space, right? We have a spinning neutron star here, and the electromagnetic radiation is coming out of the rotating axes. It's like a lighthouse. You can only see it if that rotational, that electromagnetic beam is hitting you. The formation of these pulsars is basically through large giant stars, right? So stars about 10 to 25 solar masses. When they collapse, they go through a supernova process. The core is compressed, right, into basically a, all the particles are basically compressed into neutrons. This process basically takes pretty much a significant amount of mass, right? Most neutron stars in the end usually are between 1.3 and 3 solar masses. That mass is then compressed into a space that's only about 10 kilometers in size. It's about the size of a city. And so as a result, all that rotational inertia basically winds up with a very rapidly spinning object in the end, the pulsar. Generally speaking, pulsars have a very high rotational frequency, at least the ones that we are looking for. We're talking on the order of milliseconds to seconds. I should also point out, just to be for completeness, not all neutron stars are pulsars. All right. The pulsar searches that Einstein at Home uses basically the Arecibo survey, and also, like I said previously, the Parkes survey. We've discovered about 50 pulsars in total. I believe the number is about 30. Excuse me. These are, and I should say, these are also radio pulsars, right? So these two telescopes are radio telescopes, and the total number of radio pulsars that Einstein at Home has contributed to is about 50. There's also the Fermi Gamma Ray telescope. This looks for pulsars that are emitting gamma ray radiation. Here the number is about 20. The searches are all basically blind searches. There's very little parameter space that is constrained. This results in a large computational parameter space, which is why volunteer computing is useful. The pulsar discoveries I've put up onto a map here of sort of the different volunteers. I don't know how well you can see it, but the idea is that the red here is Arecibo. So, for example, we have different volunteers located in red on the map, or have helped contributed specifically to finding specific pulsars. I'll discuss this in a little more detail in a moment. jumping over to the gravitational wave searches, LIGO is the Laser Interferometer Gravitational Wave Observatory. This collects gravitational wave data. The two sites I've listed here are in Hanford, Washington, and Livingston, Louisiana. The gravitational waves were first basically discovered, quote unquote, observed in fall of 2015. Those observations that the LIGO observatories are currently have currently found, and was probably in that BBC article that we were on that website, have generally been through black hole mergers, or binary black hole mergers. What Einstein Home is looking for is what's called a continuous wave search. This is a more challenging search because basically the idea is if you have a spinning neutron star or a pulsar, and if it's not symmetric, it's going to be emitting gravitational waves. This is a sort of a schematic that I show in a number of public talks. It's the size of a neutron star over the city of Milwaukee. Milwaukee is smaller than the city of Chicago, but it's about the size of a city. Is how large this object is, but it's very, very heavy. There's nothing that says that this neutron star has to be symmetric. This object that is about the size of a city, that's about, say, 2 solar masses, it is probably going to be deformed. And this is actually very similar to how the Earth itself is actually deformed. The Earth is actually not a sphere, right? It's an oblate elliptoid, for those who care. Basically, the idea is that as the Earth spins, the North and the South Pole get compressed, right, while the area around the equator bulges a little. So this, if a neutron star has a similar asymmetry, you can generate gravitational waves. What do I mean by that? Well, the science, honestly, there's a lot more math than I can explain, but the science states that a symmetric object that rotates doesn't actually generate gravitational waves. You have to have some kind of asymmetry in order for a gravitational wave to be emitted. This is why if you have, say, 2 black holes rotating with one another, right, there's an asymmetry in that system, the rotation. The other alternative that I'll quickly mention is that if there's some kind of deformity on the surface of the neutron star, right? So in this case, in this case, quote mountain unquote here in the corner. If this object is not symmetric, that can also contribute to gravitational wave production. Einstein Home basically uses the public LIGO data from the first 2 observing runs, known as 01 and 02, to basically do this continuous wave search. So onto the technology points. So why are we using volunteer computing? All these searches that I kind of mentioned are very, very large in parameter space. They're very, very difficult because you basically have to search the whole sky. These spinning objects have multiple frequencies, so you have to search all frequency spaces. So and then coupled with the fact that you also have to take into the fact that the Earth is rotating, the Earth is actually revolving around the sun. Suddenly, you have a very computationally difficult problem. The other reason is actually, frankly, outreach, right? This is in some ways a way to sort of inform the people who pay our bills, right? This is all publicly funded research. This is a way to kind of tell them, or at least let them know what they're paying for. What lessons we've learned in using BOINC for our voluntary computing? Well, we try to test everything before we publish, right? So there's a lot of testing that happens locally. There's a lot of testing that happens through the use of sort of a public beta applications that are first distributed to our volunteers. Our volunteers tend to, then give us feedback on, what happens with these betas. Oliver gave a talk about 10 years ago now about having a very healthy MySQL database and sort of tuning your MySQL database to optimize its effects. I would recommend you look at his talk for the details of this. There's a lot of monitoring of the server, of our network use, and things of this nature. We try to solicit help from our volunteers. I was mentioning with those public betas. This is something that that we try to do to try to keep them engaged and informed. I also mentioned here in this last sentence, there's a lot of unique changes and a sort of unique elements to Einstein at Home that we use to sort of achieve our goals. If you're interested in this, we can talk about this after the talk. We try to keep ourselves sort of in the public eye, if you will, so that every time sort of Einstein at Home anytime there's some kind of discovery that uses Einstein Home, we try to get ourselves credit. This is a link to a fairly large poster that was NASA produced for about the Fermi telescope. Einstein Home is featured. It's sort of in a little blurb in the corner. We did try an email newsletter. It didn't really work. It worked to the extent that, it did what it did. That being said, there's only so many people, and we have only so many man hours that we can work on this project. We do have a very active forum community, and I can thank Richard in person now for being such a wonderful volunteer and really engaging with our other users, because they do things such as point out problems and work on these beta applications. We actually publish things, which I think sort of what we were talking about, climateprediction.net. This is a tangible scientific goal. We're in a world where you have to publish your results in scientific journals. As a result, we're actually able to give credit for the discoveries, right? I showed you this map earlier. I think I show it again. So the idea is being that if you participate in, say, the Fermi gamma, if your computer was crunching the data from the Fermi Gamma Ray Telescope that happened to discover a pulsar, we can kind of trace back and know who you are. So in the paper, we can then say, so-and-so from Kiel, Germany, and so from Martinez, California, are actually, quote, responsible for finding this pulsar. And so this is actually from, one of our publications. And in addition, oops. I thought I managed to put the slide up, but in addition, the people who actually do discover the pulsars actually receive, a certificate of pulsar discovery, if you will. So in the end, of course, I have to, point out that this is a project that is funded by a random icon that could not be found. That was supposed to be from the National Science Foundation, but I guess they're not really important. I guess Max Planck Institute is the only one that funds us. My apologies. So, of course, people like Bruce and Bernd and Oliver, Benjamin, who does a lot of the outreach and a lot of the slides, information from the slides comes from him. And so I'll end with that just by asking if there are any questions. Hold your applause, please.
There's a question from the stream. Can we get badges on Einstein at home?
Badges on Einstein at home. Richard brought up badges earlier. Actually, the answer, the short and the long answer is the problem is not the technology. The problem is what you do with the badges, right? So I will talk to, maybe I'll talk to Richard about this later, frankly.
What would you say are the largest scaling hindrances for Einstein? Is it on your side, the server side, or is it the lack of volunteers?
So the question is, what are currently our largest scaling challenges with Einstein at home? Bernd, I might actually have to point this at you.
I think we could certainly do with 5 or 10 times as much as volunteers or computing power. So this is neither an issue for providing the work nor for our servers. So if it gets to that, I don't see that much of a challenge. Our servers are pretty underloaded, if you want to say so. So if yeah, I don't see a very. The challenge is more to actually get the volunteers or get the computing power that we could use, and to attract volunteers or to gain them.
Any other questions?
I want to have a question that maybe could go for you, both project presentations. How do you find a way to help the volunteers to feel like this is really important work and it's something that's worth doing? Like what does that outreach look like, and how do you do that? Now, it's super cool, right? take that other step of it making it feel like, wow, it's really worth these computers sitting out all the time and me paying attention to it.
So just to repeat, the question is, how do we, in terms of volunteer retention, how do we try to convince them that this project itself, that the science itself, if you will, is fairly important? I can speak for Einstein at Home. I think for a lot of people at Einstein at Home, and I'm just generalizing, and honestly, this is my personal guess, is it really is the coolness factor of outer space. That I think that is kind of what at least attracts people at first, and sort of gets them hooked, if you will. I don't know if you guys at Climate Prediction have another answer.
So for climate prediction, I suppose the key thing is that, well, it is a grand challenge problem. So from that point of view, because we try to do as many of these analyses of events in real time, the attribution studies, as possible, then it's events that people can relate to. So, for example, the French heat wave has been on, I think, about 15 different TV networks around Europe. It will be some sort of nature equivalent publication when it comes out, all of that sort of thing. And then again, linking it back to how have people contributed. So one of the things then, the difficulty we have is we've only had a specific comms person for a small number of months over the entire duration of the project, so over 15 years. And that sort of thing really helps, because one of the things, the comms people that have talent that can do journalistic style comms are few and far between. They're very expensive, and they normally end up going off to do different things. Being a journalist, I think one of ours was historically, and so it falls on us within the project to do that, and we're not very good at that. I can't write a compelling piece that's going to really capture the heartstrings. So in some ways we then link to Twitter and we try and use our social media and all this, but we're not great at it. We're not great at it. We do sort of rely on the fact that what we're doing is quite important. So we're complacent, I suppose you might even say, over some of this. We have certainly attempted to on multiple occasions. That can sometimes not make the final cut of any press release. But if there's an interview, we've been working on our faces, i.e. those members of the scientific team that normally end up being those on TV or radio, to actually get them to say something relevant to make sure that it highlights. But so for example, that BBC News piece had a link through to climate predictions on that. And I must admit, I've got to go and listen to that piece now to see actually how well we're mentioned.
Richard, you had a question?
Well, just to follow on the volunteer recognition thing, Einstein has home some years ago is in a position where your results are very few and far between. You had the number of 20 pulsars discovered in an entire study, and you were able to reward, if you like, individual volunteers by name with the presentation of certificates. And that doesn't work, obviously, for other BOINC projects where it's an aggregate, broad result comes across, which is one thing where badges on websites are very popular. Badges for finding a pulsar wouldn't really work very well. So one has to consider a range of things, and there's nothing that beats active involvement and feedback from project administrators, possibly via moderators, to the volunteers on the project websites and message boards.
Good point. Anything else?
Yeah, one more.
Oh, no. Someone recently told me that at LIGO, the way they test it is they go up and kick the machine. Is this true?
The question actually was about LIGO, whether or not they kick the machine to test it. I unfortunately do not know the operations side of things over at LIGO. I'm unfamiliar with what they do. That being said, it is a very, very sensitive detector, right? The entire reason why one is in Hanford, Washington State, and the other one's in Livingston, Louisiana, is specifically for this purpose, so that if there's any kind of seismic event in one, you have to be able to correlate it with the other.
Literally two sentences. I mean, you can jump. You can jump on the ground, say half a mile away, and it will detect it. I mean, we have a small detector running in Hanover, in the middle of Germany, and we still see the waves of the Northern Sea. And we can monitor the trade schedule of trains going.
To actually tie this into the question about outreach, this kind of information is really fascinating to a lot of people. Like, it brings it to a human level. It's not necessarily that you're searching for pulsars and you can't find it, but you can detect the waves from miles away. That's just interesting to people. Like, okay, I'll go detect the wave.
Question?
Maybe we actually try to get rid of this. Exactly what we thought was, but actually, it's still something.
Yeah, go ahead.
So I was always fascinated. I heard Bruce describing this stuff a long time ago as, like observations of the universe have traditionally always been done through the electromagnetic spectrum, and being able to observe through the gravitational spectrum is a new thing. And I always found that on the basis fascinating. I'm wondering if you have any visualizations of like, what does the universe look like in gravitational waves? Like, do you have pictures of these, what comes out of the telescope?
So the question is, do we have any visualizations of the gravitational wave data? The answer is yes, we do. If people really want to see it, I can pull it up, but it'll take me a few minutes to try to find one. Actually, no, it won't. Actually, it'll take me 30 seconds because I know where one is. But the point being is that I can show you the visualization, what comes out of the detectors, right? And so let me see if I can go find a web browser. I can't spell Wikipedia correctly, but hopefully it'll figure it out. And then I know for example for public consumption, what they did was they even took that. They can take this this data and then make it, and they created a sound wave out of it. And when the first detection occurred, and after the first detection occurred in the spring of 2016, the people at NSF went in front of Congress and they played that tape, and that was a big the congressional committee was quite happy with that. But perhaps this was something that people were saying, is that something that puts something like this. I can talk about colliding black holes, but that puts it into a much more human scale, right? I mean, it's a here we go. Well, while we wait, what you're going to see here is basically the what we're talking about here. So it's a laser beam that gets split in half and comes back together, right? And so the distance of the two arms, if everything is completely noiseless and there's no detection, the distance should be in effect the same. They should cancel out. If they don't cancel out, you'll see in effect the interference pattern. And what you're seeing here, in effect, is that interference pattern from the two detectors. There we go. Right. So again, Hanford, Washington, right? This what's called, they call it the strain, and that's what it looks like. And then as you have two objects that basically they're spinning around each other, then they collide, right? So they as they spin, they get faster and faster and faster, and that's why you see the strain increasing over time. And then the collision occurs. There's a little bit of a ring down, and then it becomes quote flat unquote again. I hope that answers your question. I want to point out, this is not what Einstein at home does. It's completely different.
Thank you. We are running about 15 minutes behind schedule, and we have a packed afternoon. No.
first of all, we don't want to interrupt the